So you've got a 2.5 megahertz band. You know that interference can be here or here.
Oh.
Never at the same time, either the upper or the lower, you don't know which, or there might not be any interference. Yeah. So you could detect and reconfigure. Yeah. The problem with detect and reconfigure is that you have a lot of overhead. So you have a lot of back and forth. It means that you need that duplex link. Yeah.
Do you know that the interference can be seen by both nodes?
Yes, you do.
So the transmitter can listen first and then choose the other node.
You could, yeah, exactly. You could put a sensor in the transmitter, so that'll be one way to do it. Yeah. And what about singular multi-carrier? What type of waveform would you use for this scenario?
Very different.
Yeah, definitely. Yeah, so OFDM makes sense for this. So one of the problems with OFDM is, having looked at the algorithms that we use for, at your receiver, the first algorithm we use for an OFDM receiver is frame detection. So the problem is, if you have a band where you have, say, for example, interference in the upper half, even though you have individual subcarriers, that first step of frame detection happens in the time domain. So that interference in the upper half is still going to banjax your frame detection. So you're not going to be able to get your frames, so that could cause you problems. So you have to find ways around that. So these are the kind of issues you have to think about. So one approach for getting around that is channelization. Okay, so obviously we know that this is effectively channelized by the type of interference we're going to have. So let's come up with a waveform that's already channelized, that's independent in the two halves. So this is one possible way you could do it. You could use IRIS for this, where you have a packet source, you have independent modulators. You can use a synthesizer. So what a synthesizer does is it takes two signals and puts them into one. So you can, you might have come across the idea of a polyphase. A polyphase filter uses a synthesizer. So what that does is it's a very efficient way of taking a number of signals and putting them together side by side in frequency. On the receiver, you can use the inverse polyphase channelizer. So it splits the signal up, does the inverse, takes the two of them, splits them into separate signals, independent demodulators, and then into your packet sync. So what you end up with is a signal that looks a little bit like this. So it's effectively two OFDM signals. So you've got one signal in the upper half, one signal in the one signal in the upper half, one signal in the lower half. In this scenario, it means that as the interference comes in line, it might knock out one or other of these two, but it's never going to knock out both because they're completely independent. So that was the qualification phase. You have to do that just to get in the first place. The next step was the wildcard selection. So from the qualification phase, some people got straight in, and some were kind of borderline, so they had to go through this wildcard selection. Similar to the first scenario, you had a single radio pair with a transmitter and a receiver. They were tested against house radios and other possible interferers, so you didn't know what type of interference you were going to be dealing with. You had to transfer a data file without errors as fast as possible, and there were two types of competitions. There was the competitive match, where you're tested against a single house radio pair and the fastest team wins, and there was a cooperative match, where there were two house radio pairs, and it was the sum of the total throughput from all of the pairs was providing the score. So one possible approach for handling this would be to build on what we already had, and this would be a more complex IRIS implementation, where you have, instead of just two independent OFDM waveforms, you could have multiple OFDM waveforms being synthesized, and you've got a transceiver system where you have two-way communication. So I talked about this polyphase filter bank. So you have an efficient way of doing that synthesis and channelization. If anyone's interested in that, some of the work by Fred Harris is well worth a look at in polyphase filters. So you could end up with a waveform that looks a little bit like this, where you have multiple independent OFDM waveforms. So I've talked a little bit about IRIS. I've talked a little bit about the types of applications you can use IRIS to achieve. I've talked a little bit about some of the more complex waveforms that you can use. Tomorrow in the in-depth session, I'll be actually building these radios. So we have a couple of live environments that I can give you. You can plug it into your laptop. You can run existing radios. You can start tinkering with it, building radios, building controllers. We'll try and do maybe a DSA application tomorrow. Who here is going to be at the in-depth session tomorrow, actually? Cool. Very good. Right. Cool. Yeah, I do have enough USB keys for everybody, so it's good. So finally, why use IRIS? There's a very quick learning curve. It's very easy to get started with and to build something interesting. It's open source. It's very easy to contribute to. It's a relatively small project still, and you can quickly implement complex systems. So the code is there, and those are my details if you want to get in touch. So this month we released version 1.1. With that release came a lot of graphical interfaces. So we have scatter plots, complex plots, real plots, waterfall displays, and so on. We started building in support for liquid DSP. So some of you may have come across this before. It's a software-defined radio digital signal processing library put together by Joe Gator in the US. It's quite powerful. It's released under GPL. So we started building on some of those components, and we now have polyphase channelizers, polyphase synthesizers built in, and Andrei Pushman, based in Germany, has done a lot of work on Mackler implementation. So the first Mackler implementation he's done is a simple Aloha Mac, where he has a ton-tap network interface running in the stack, a Mackler running Aloha, and then using OFDM modulators and demodulators in your transmit and receive chain. So simple Aloha is just sending a packet, waiting for an ACK, you receive the ACK in a timeout, and then you resend the packet. So it's just quite a simple implementation as a first go. And all of his code is also up on GitHub, so you can find that there. So that's it. That's pretty much the overview of IRIS, what you can do with it and what you can't. Any questions?
Yeah, you speak a lot about modulation and demodulation, but
sure.
If you look at all modern communication systems, they have a quite advanced error codec.
Sure.
Do you also handle error coding schemes?
We do, yes. So Phil Kern wrote a very good library called just a forward error correction library. So we build on top of that, and we have a couple of forward error correction schemes built in.
Do you support turbo coding on LTPC?
Not yet, no. No, we need to though.
Then I was wondering, for the systems that you study, what are the data rates that you can handle?
Sure. So using the processors that we have in our current laptops, you get the peak bandwidth that you can handle using our OFDM modulators and demodulators about 8 megahertz.
Yeah.
So you're getting a data rate of 8 megasamples a second. So that's pretty much your peak data rate. So if you're going QPSK, you've got double that. Yeah.
So you say laptop, so that's really on a Pentium processor?
Yes, yeah. Or
okay.
A Core i3 or an i7.
Yeah, okay. Yeah, thanks.
No problem. It's interesting actually you bring up the data rates and the turbo decoding, because there's a lot of interest recently in LTE. So LTE as a standard is, I've called it the killer application for software radio, because it's quite nice to try and implement as a software radio. Have you come across Marisoft or Fabrice Bellard, a programmer?
No.
So Fabrice Bellard is this rock star French programmer who basically went into his basement, and in the course of about 3 months, at the end, came out with an LTE eNodeB base station, written in his own version of C, which runs on an Intel Core i7. So if you get a USRP N210, link it up to a Core i7 processor, you can run a full LTE eNodeB.
Is that for femto cells or also for bigger?
Also for bigger cells, yeah. So I think you can handle a maximum of 4 users, so it's probably more suited to femto cells. But the fact that he could get the coding rates and get the turbo coding working on a Core i7 is very, very impressive. And then Marisoft is the company that he's commercializing that through.
Yeah.
So unfortunately, everything he's done until now has been open source, and that this is closed source.
Yeah.
But LTE is interesting as well because there's...
Yeah, it's very flexible. You have lots of modes.
Yes. But there are quite a few open source projects working on LTE. So you've got GR LTE for GNU Radio, you've Open LTE, and I'm working with a coder called Ishmael Gomez on a library for LTE, so liblTE, which we're hoping to provide the DSP necessary for LTE eNodeBs and handsets.
Yeah. Okay.
That's good. Any other questions? Yeah?
Latency issues with the Ethernet connection to the US
You do, definitely. Yeah. So that's one of the limitations with it's one of the problems with software radio generally is the issue of latency. So it's one of the reasons why it's incredibly difficult to do Wi-Fi, for example, So Wi-Fi is, if you look at Wi-Fi as a standard, it's really not suited for software radio implementation because of latency issues. So Wi-Fi has this really, really fast turnaround for collision detection. So if you're trying to achieve that turnaround with any sort of a bus between your front end and your processor, you won't be able to do it. So people who have done Wi-Fi implementations with software radio in the past have used PCI interfaces, for example. I think the guys in Microsoft did something like that. But with something like LTE, the latency restrictions at the node itself aren't so stringent, so they are more achievable.
How did the guys in the Microsoft handle this latency issues?
That's a good question. I don't know. Yeah, that's the problem because it's so closed source. We can't find out. Yeah, but like I say, the latency issues for LTE are not as stringent as they are for Wi-Fi.
Yeah. That's cool.
Yeah, but still they're there. Yeah. So you have a lot of questions about how they achieved some of the things they achieved. Yeah, so the coding, the turbo decoding, getting that to work in real time is impressive. Yeah. But this guy Fabrice Spellar, he doesn't write in C. He wrote his own compiler in a subset of C, so it's blisteringly fast. Yeah. It's impressive. Cool. So if there are no other questions, I'll finish up there. Thanks very much.
Thank you.
And even if you're not going to be at the in-depth session tomorrow and you'd like to try out IRIS, let me know. I have USB 3 keys with the live operating system environment and IRIS fully installed, so it's quite easy to get up and running with.
Okay, I think we finished the morning session. Dan, can we have now break for lunch? Is it
Yes.
the right timing?
Yes.